of the 2025 internal pure chemistry paper 2. So without any further ado, let's look at question number 1. So question number 1 reads, so this question is all about safety, particles, and diffusion. So part A asks us to give 2 safety precautions to be taken when carrying out an acid-base titration. So titration involves the handling of acids and alkalis, which can be corrosive, so safety is always matters here. 2 good precautions are wear safety goggles to protect your eyes from splashes and wear a lab coat. Alright, so moving on to question B, question 1B. So question 1B tells us that particles in the states of matter are always moving. Particles in a state of matter are always what? Moving. But B1 asks us which theory supports this fact? Which theory supports this fact? So the answer is the kinetic theory of matter. So this theory explains all particles, whether in solid, liquid, or gases, are in what? Constant motion, and the amount of energy they have determines how they move. Alright, so moving on to question B2. So question B2 asks us to describe the type of movement of particles in solid. Describe the type of movement of particles in solids. So in a solid, particles are held closely together in a fixed positions, so they cannot move from place to place. Instead, they vibrate about their fixed position. That's a key word to remember: vibrate and not move freely. Okay, moving on to question C. So question C is all about diffusion, since gases diffuse at different rates. So let's look at question C1. So question C1 asks us what is meant by the term diffusion. What is meant by the term diffusion? So diffusion is a movement of particles from a region of higher concentration to a region of lower concentration until they are evenly spread out. This happens because particles are in constant random motion. Alright, so moving on to question C2. So question C2 gives us a practical scenario. Gases A and B are colorless, but react to produce a yellow band, which is a solid. We are told the relative mass of A is double of that of B, and we need to show on the diagram where the yellow band would form. So here, how to think about this is step by step, is that light gases diffuse faster than heavier gases. Since gas B has half of the molecular mass of gas A, gas B is lighter, so it diffuses faster and travels further before meeting gas A. So this means that the yellow band will form closer to the source of gas A, not in the middle of the tube. So when you are marking this on the diagram there, the place where the yellow band should be near to the source of A, because B has traveled further to meet it. So that completes question A1 with 6 marks. Let's move on to question A2. So question A2 reads, so question 2A2 shows us a diagram of an experiment for separating mixture Q, where the mixture is heated and passed through an apparatus before being collected rather. So part A asks for the name of the separation technique shown in the diagram. So looking at the setup there with a heating, a condenser, and a collection vessel, this clearly shows that this is what? A simple distillation. So that's the answer. The setup there shows what? A simple distillation. Okay, so but then moving on to part B. So part B asks us to name the apparatus A and state its function. So the apparatus A, the piece with the water flowing through it, is called a condenser, and its function is to cool the hot vapor so that it condenses back into a liquid, which can be then corrected. Okay, moving on to question part C. So part C asks us to label the water inlet and outlet on apparatus A. So the rule here is that the water always enters at the bottom of the condenser and leaves at the top. This is so that the condenser fills completely with water, giving the most efficient cooling, working against gravity rather just running straight through. Okay, moving on to question D. So question D reads, give one industrial use of this separation technique. give one industrial use of this separation technique. Okay, so a great example is a distillation of sewer water to produce fresh drinking water, or the refining of crude oil through fractional distillation, which works on the same cooling and condensing principle. Okay, that's question A2 done. 5 marks, just like that. Now let's move on to question A3, which deals with the atomic structure. Okay, so question A3, part A asks us to complete a table to deduce the number of electrons and the number of neutrons in two ions given, namely the nitrogen ion and the gallium ion. So let's work through the nitrogen first. So the bottom number 7 is a proton number, which tells us that nitrogen normally has 7 protons and 7 electrons, but this is an ion with a 3 minus charge, meaning it has gained 3 extra electrons. So the number of electrons is 7 plus 3, which gives us 10 electrons. So the neutrons will take the mass number 15 and subtract the proton number 7. 15 minus 7, this will give us 80 neutrons. Now for gallium. So the gallium, the proton number is 31. So gallium normally has 31 electrons, but this ion has 3 plus charge, meaning it has lost 3 electrons. So the number of the electrons is 31 minus 3, which gives us 30, which gives us 28 electrons. So for the neutrons, we take the mass number 71 and subtract the proton number 31. 71 minus 31 gives us 40 neutrons. So to summarize, the nitrogen 3 minus has 10 electrons and 8 neutrons, and the gallium plus 3 plus has 28 electrons and 40 neutrons. Then we're moving on to question B. Question B asks us to draw a structure of the nitride ion showing all electrons. So nitrogen has 7 electrons normally, arranged as 2 in the first shell and 5 in the second shell. As 3 minus ion, it gains 3 more electrons, giving a total of 10 electrons, arranged as 2 in the first shell and 8 in the second shell, which now is a full outer shell, just like neon. When drawing this, show the nucleus with the symbol N and the charge 3 minus, with two electrons in the inner shell and 8 electrons in the outer shell. Often shown, and most of the time this is shown as dots and crosses to represent the original and gained electrons separately. That's question A3, 6 marks. Okay, let's move on to question A4, a calculation question. A calculation question. So question A4 tells us that Elena reacted 0.765 grams of aluminium oxide with 100 cubic centimeters of 0.1500 moles per cubic decimeter of sulfuric acid and collected 1.368 grams of aluminium sulfate. A asks us to construct a chemical equation for the reaction, including state symbols. So aluminium oxide reacts with sulfuric acid to form aluminium sulfate and water. Let's balance this step by step. We start with aluminium oxide, which is Al2O3 plus sulfuric acid, which is H2SO4, reacting to form aluminium sulfate. Al2 open bracket, so open bracket SO4 close bracket 3 plus water, which is H2O. To balance it, we need 3 sulfuric acid molecules to provide the 3 sulfate groups, and that gives us 6 hydrogen atoms, which form 3 water molecules. So the balance equation is Al2O3 plus 3H2SO4 will give us Al2 open bracket SO4 close bracket 3 plus 3H2O. Adding state symbols, aluminum oxide is solid, sulfuric acid is aqueous, aluminum sulfate is aqueous, and water is liquid. Then moving on to question B. So question B asks us to determine the limiting reagent in this reaction. Determine the limiting reagent in this reaction. So it's here. So here's how we approach this step by step. First, calculate the moles of aluminum oxide. The relative molecular mass of Al2O3 is 27 times 2 plus 16 times 3, which gives us 102. The moles equation, moles equals to mass divided by molar mass. So 0.765 divided by 102 gives us approximately 0.0075 moles of aluminum oxide. Next, we calculate the moles of sulfuric acid. Moles equals to concentration times volume in cubic decimeters. The volume is 100 cubic centimeters, which is 0.1 cubic decimeters. So moles equals to 0.1500 times 0.1, which gives us 0.015 moles of sulfuric acid. Now compare this to the equation ratio. From the balance equation, 1 mole of aluminum oxide reacts with 3 moles of sulfuric acid. So 0.0075 moles of aluminum oxide would require 0.0075 times 3, which is 0.225 moles of sulfuric acid. But we only have 0.015 moles of sulfuric acid available, which is less than what's needed. This tells us that sulfuric acid is a limiting reagent because it would run out first. Moving on to part C. Part C asks us to calculate the percentage yield of the product. Calculate the percentage yield of the product. So first we calculate the theoretical yield based on the limiting reagent, sulfuric acid. From the equation, 3 moles of sulfuric acid produces 1 mole of aluminum sulfate. So 0.015 moles of sulfuric acid would produce 0.05 divided by 3, which is 0.005 moles of aluminum sulfate. The molar mass of aluminum sulfate, which is Al2 open bracket SO4 close bracket 3, is 27 times 2 plus sulfur 30, 2 plus oxygen 16 times 4, all multiplied by 3, giving a total molar mass of 342 grams per mole. The theoretical mass equals mass times molar mass. So 0.005 times 342 gives 1.71 grams as the theoretical yield. So the percentage yield is equals to actual yield divided by theoretical yield times 100. The actual yield given was 1.368 grams. So 1.368 divided by 1.71 times 100 gives us approximately 80%. That's question A4 complete. 8 marks in total. Now let's move on to question A5, which uses the periodic table. So question A5 part A is about group O elements, which include helium, neon, argon, and krypton, and xenon. So part A1 asks for the common name of these elements, and these elements are called the noble gases. But A2 asks for one use of helium. Helium is commonly used to fuel the balloons and the airships because it's much less dense than air and is non-flammable, unlike hydrogen. Okay, moving on to question A3, which asks us to explain why these elements are monoatomic. Noble gases, why these elements are monoatomic. So listen closely. Noble gases exist as single atoms because they are already have a full outer shell of electrons. This means they are extremely stable and unreactive. So they have no tendency to bond with other atoms or even with each other. Alright, so that's the answer there. Then moving on to question B. Question B tells us that the transition metals are found between group 2 and group 3 of the periodic table. Then part B1 asks us what type of oxide these elements form. So transition metals form basic oxide through, though some can be amphoteric depending on the specific metal. Then move on to part B2, which asks for the two properties of transition metals. So the good answers may include they have high melting, they have high melting and boiling points. They are good conductors of heat and electricity. they form colored compounds, and they often show variable oxidation states. Any of any two of these will earn the full marks. So that's question A5 finish, 6 marks. Now let's look at question A6, which is about the displacement reaction. So question A6 tells us that aqueous bromine reacts with aqueous potassium iodide in displacement reaction. So part A asks us to construct an ionic equation for this reaction. So let's build this step by step. Bromine is more reactive than iodine, so bromine displaces iodine from the potassium outside. In ionic terms, we only show the spaces that are actually changed. So bromine as Br2 gains electrons from the iodine ions, which loses electrons to become iodine. So the ionic equation is Br2 plus 2I minus we give us 2Br minus plus I2. Notice the potassium ions are restricted ions and are left out of the ionic equation entirely. Okay, moving on to question B, part B. So part B asks us to state and explain one observation made during this reaction. So question B asks us to state and explain one observation made during this reaction. So the observation is that the colorless or pale yellow bromine solution changes to brown solution, or you might see the solution turn brown or dark orange. The explanation is that iodine is being formed in solution, and iodine gives a brown color aqueous solution. So moving on to question C. So question C asks us to explain how an increase in temperature increases the rate of this reaction. Here's a step-by-step reasoning. When temperature increases, the particles gain more kinetic energy, so they move faster. This means particles collide more frequently, but more importantly, a greater portion of particles now have energy equal to or greater than the activation energy. So a higher percentage of collision result in a successful reaction. Both of these effects combine to increase the rate of reaction. So that's your answer there. Then moving on to part D. So part D asks us to state whether the bromine is oxidized or reduced in this reaction. So looking back at our ionic equation, bromine starts as Br2 with an oxidation state of 0 and ends up as Br minus with an oxidation state of -1. Since its oxidation state decreases, bromine has gained electrons, which means bromine is reduced. And that's question A complete, 7 marks. I hope you are learning one of the things. Please, if you haven't subscribed, do so. If you haven't liked, please do so. If you haven't commented, please do so. If you haven't joined our online classes, please do so by WhatsApping me on the number shown on the screen there. All right, so let's move on to question 7. Okay. So question A7, aqueous silver nitrate AgNO3 in aqueous solution is electrolyzed in inert electrodes. Part A asks us to write the formula of all the ions present in the electrolyte. So silver nitrate becomes into what? Silver ions Ag positive and nitrate ions as NO3 negative. But this is an aqueous solution. Water itself is also partially ionized, giving us hydrogen ions H positive and hydroxide ions as HOH negative. So together, the four ions present in a Ag positive, the four ions present are Ag positive, NO3 negative, H positive, and OH negative. Don't forget that the water derived ions, they are easily missed out but are required for the poverty marks. So always know that if something is aqueous, always add the hydrogen ion and the hydroxide ions. Okay, moving on to question B. So part B asks us to construct chemical equations including set symbols for the electrode reaction. Okay, asks us to construct chemical equation including set symbols for the electrode reaction. So part B1 asks for the cathode reaction. So the cathode is the negative electrode, where positive ions are attracted and gain electrons in a process called reduction. We have two positive ions variable. We have two positive ions available. silver and hydrogen ions. Since silver is less reactive than hydrogen, silver ions are discharged in preference, meaning that they are discharged first. So the equation is built like this. One silver ion in aqueous solution gains one electron to form one neutral silver atom deposited as a solid written out. Thus, Ag positive aqueous plus Me minus giving us Ag solid. That's how I write the equation there. Then part B2 axis for the anode reaction. Part B2 axis for the anode reaction. So the anode is a positive electrode where negative ions are extracted and lose electrons in a process called oxidation. We have two negative ions available, nitrate and hydroxide. Nitrate ions are very stable and are not discharged. So hydroxide ions are discharged instead. So hydroxide ions are discharged instead, releasing what? Gas, releasing oxygen gas. The equation step by step is that 4 hydroxide ions in aqueous solution lose 4 electrons, forming one molecule of gas of oxygen gas and 2 molecules of water, written out as 4HO negative, the negative charge in aqueous state. It gives us 2 oxygen gas plus 2 H2O liquid plus 4 E minus. That's right. That gives us question A7. That gives us the entire answers for question A7 and the 6 marks. Now let's look at question A8, our final question in section A. So question A tells us that the sodium, potassium, and rhodium and rubidium are some of the elements found in group 1 of the periodic table. So part A asks us to give a reason why they are all found in this group despite having different atomic numbers. The reason is that they all have one electron in the outermost shell. Elements are grouped according to the number of electrons in their outer shell, not according to their atomic number. So part B asks us to explain why potassium is more reactive than sodium, despite being in the same group. So here the answer is that potassium has one more electron shell than sodium, which means its outermost electron is further from the nucleus. Because it's further away, the attraction between the nucleus and that outer electron is weaker due to increased shielding from the extra inner shells. This means the outer electron is more easily lost in potassium than in sodium, which is why potassium reacts more vigorously than sodium. Okay, moving on to question C. So question C reads, construct a balanced chemical equation for the reaction of sodium metal and cold water, including state symbols. So sodium reacts with cold water to produce sodium hydroxide and hydrogen gas. The balance equation is 2Na in solid state plus 2HO H2O in liquid state will give us 2NaOH aqueous plus H2 gas. Notice we need 2 sodium atoms and 2 water molecules to balance the hydrogen atoms produced as hydrogen gas. Moving on to part D. Part D asks us what term is given to the oxidized and hydroxides of metals. What name is given to the oxidized and hydroxides of metals? The answer is that they are called bases. What term is given to the oxidized and hydroxides of metals? The answer is that they are called what? Bases. If they are soluble in water, they are more specifically called alkalis. That brings us to the end of section A, which is question 8 with 6 marks. Okay, moving on to section B. Section B, let's start with question number 9. So question number 9 tells us that both lead carbonate and lead sulfate are insoluble in water. So part A asks us to state the suitable method of preparing such salts, since both salts are insoluble. The suitable method is precipitation, sometimes called double decomposition. That is a suitable method. Moving on to question B. So question B asks us to describe and outline how pure dry lead sulfate would be prepared and collected, starting from lead carbonate and selecting from the given reactants, which is lead carbonate solid, dilute sulfuric acid, dilute nitric acid, sodium sulfate, and distilled water. So let's go through this step by step as a full method. So step number 1, lead carbonate does not dissolve in water, so we cannot react it directly with sulfuric acid to get a clean reaction. Since lead sulfate is also insoluble and would cause the lead carbonate stopping the reaction. So instead, we first dissolve the lead carbonate using dilute nitric acid since lead nitrate is soluble. Add excess lead carbonate solid to the dilute nitric acid and stir until no more dissolves, forming a solution of lead nitrate. Step 2, filter the mixture to remove the unreacted excess lead carbonate. Since we added it in the excess to make sure that all the acid was used up, this leaves us with a clear filtrate of lead nitrate solution. Step 3, add this lead nitrate solution to dilute sulfuric acid or to a solution of sodium sulfate. A precipitate of lead sulfate forms immediately because lead sulfate is soluble. Step 4, filter the mixture again to collect the lead sulfate precipitate. Step number 5, wash the precipitate with distilled water to remove any soluble impurities such as leftover sodium nitrate or nitric acid. Step 6, dry the precipitate ideally between sheets of filter paper or in a warm oven to obtain pure dry lead sulfate. That's a full 6 marks method right there. Moving on to question part C. Part C asks us to explain why the lead salts are not prepared by the acid-alkali titration method. The reason is that most lead salts, including lead sulfate and lead carbonate, are insoluble in water. The titration method only works for the prepared insoluble salts since it relies completely dissolving both the acid and the bases and then evaporating the solution to crystallize the salt. Since lead salt does not stay dissolved, this method simply does not apply. Okay, moving on to part D. Part D asks us to state the chemical test for the sulfate ions. So the test is to add dilute hydrochloric acid followed by barium chloride solution to the sample. If a white precipitate forms, this confirms that the presence of sulfate ions, since barium sulfate is insoluble and forms this white precipitate. So that's question B9 complete. 10 marks, just like that. Now let's move on to question B10, which covers the bond energy and enthalpy changes. Alright, so question B10 gives us the equation. Hydrogen gas plus fluorine gas produces 2 hydrogen fluoride gas. Part A asks us to construct an equation using structure formula showing the bonds. This means instead of writing H2 plus 4 plus F2 arrow equals to 2 HF, we draw each molecule showing the single bond between the two atoms. So H, you have the bond with another H plus F with another bond F will give us two separate F with separate H with F molecules, each showing a single bond between the hydrogen and the fluorine atoms. Part B refers to the bond energy table, which gives us H connected to H bond plus 436 kilojoules per mole of F to F bond as plus 138 kilojoules per mole and H to F bond as plus 562 kilojoules per mole. Then part BI asks us to calculate the enthalpy change, which is delta H for the reaction. So let's walk through this step by step. Grab your pen and paper. Please, if you haven't subscribed, please subscribe. If you haven't liked, please like. And please, if you have any question why you feel you are stuck in this past paper video, please comment so that I can help you or give you exactly same number. Make sure to state the question number and the exact part of the question, then state why you're not understanding. Don't just leave the don't just come out and comment the exact problem. No, I don't understand why the answer is coming from. How can you comment like that? How will I know if you're watching this question number, this or question number one? So please make sure you read the question number and the part of the question, so that at least when I'm responding to you where you have the question, I can know exactly where to go. Thank you. Now let's continue with our calculation. Alright, so step number one, calculate the energy needed to break the bonds in the reactants. We break one H to H bond and one F to F bond. That's 430. 6 plus 138, which gives us 594 kilojoules per mole absorbed. Step number two, we need to calculate the energy released when the bonds in the product are formed. We form two H to F bonds, so that's 2 times 562, which gives us 1124 kilojoules per mole released. Step number three, calculate the delta H using the formula energy absorbed minus energy released. That's the 594 minus 1124, which gives us minus 530 kilojoules per mole. Since the answer is negative, this tells us the reaction is what? Exothermic. Please, if you haven't watched a video on how to draw these energy profile diagrams, please do comment in the comment section so that I can send you the link of a video on how to draw these diagrams. Or you can watch this video where I will teach you how to draw it as well. Okay, meaning it releases what? Energy overall. Okay, moving on to question B2. So question B2 asks us to draw an energy profile diagram for the reaction, labeling the reactants and products, delta H and the activation energy as EA. Here's how to picture this diagram. So on the vertical axis, we have the energy, and on the horizontal axis, we have the progress of the reaction. Since reaction is exothermic, the reactions start at a higher energy level, or in other words, the reactants will be what? On top. And on the left side of the graph, the curve then rises up to a peak, which represents the activation energy. That curve simply represents what? Activation energy. And before dropping down to a lower energy level on the right side where the product sits. So when you're doing the diagram, the energy profile diagram for the exothermic reaction, just know that the reactants are always on top, then the product are always at the bottom. Or in other words, I like calling it as a normal one, because we know that the product should always be at the end. So which means the opposite is true for the endothermic. The products will be on top, the reactants will be at the bottom. You have learned one or two things there. If you have learned something, please comment and let other people know what you have learned in the video. Alright, so moving on to the question. The activation energy, which is EA, is labeled as the vertical distance from the reactants up to the peak of the curve. Delta H is labeled as the vertical distance between the reactants energy level and the product's energy level. In short, the distance between those two, that's where the delta H is what is placed. Alright, moving on to question C, which is access to definitions. But C1 asks what is meant by the activation energy. So activation energy is simply the minimum amount of energy that colliding particles need in order to react successfully. So activation energy is the minimum amount of energy that colliding particles need in order to react successfully. Then part C2 asks what is meant by the term bond energy. What is meant by bond energy? So bond energy is the amount of energy required to break one more of the particular covalent bond in the gaseous state. Moving on to D. D tells us the reaction is then catalyzed and asks us to show EA2 for the catalyzed reaction on our diagram. When a catalyst is added or is used, it provides an alternative pathway with a lower activation energy. So on the same diagram, you would draw a second curve with a lower peak than the original one, meaning that just beneath it, you draw the label. Label this lower peak as EA2, showing that less energy is needed to start the reaction when a catalyst is present. And that's question B10 complete. 10 marks. Now let's move on to question B11. So question B11 tells us that a learner was provided with compound X, dilute hydrochloric acid to prepare gas Y, and that gas Y is used by plants during photosynthesis. Since the gas is used in photosynthesis, this tells us straight away that gas Y is carbon dioxide. And since we are using dilute hydrochloric acid to prepare it, compound X must be a carbonate, mostly calcium carbonate, sometimes written as the marble chips or limestone. Okay, part A asks us to write the chemical formula for compound X and gas Y. Compound X, calcium carbonate, is CaCO3. Gas Y, carbonate dioxide, is CO2. Then part A asks us to construct a balanced chemical equation for the reaction of compound X and dilute hydrochloric acid. So let's build this step by step. So calcium carbonate reacts with hydrochloric acid to produce calcium chloride, water, and carbon dioxide gas. The balance equation is CaCO3 plus HCl gives us CaCl2 plus H2O plus CO2. We need two hydrochloric acid molecules to balance the two chlorine atoms in calcium chloride. Then moving on to question B. Question B asks us to describe the chemical test of gas Y in the laboratory. Describe the chemical test of gas Y in the laboratory. So the test for carbon dioxide is to bubble the gas through lime water. So the test for carbon dioxide is to bubble the gas through lime water. The lime water turns cloudy or milky white. This confirms the gas is carbon dioxide. Moving on to part C. Then part C1 asks us what method is used to collect a dry sample of gas. Carbon dioxide is collected by downward delivery, sometimes described as a collection over a trough using a gas syringe. But more specifically, for a dry sample, you would pass the gas through a drying agent such as concentrated sulfuric acid, then collect it by downward method delivery. Okay. Moving on to question C2. So question C2 reads or asks us why this method is suitable for collecting gas Y. Why this method is suitable for collecting gas Y. This method is suitable because carbon dioxide is denser than air. So it sinks and displaces the air downward and out of the collection vessel without needing to dissolve in or react with water. Since carbon dioxide is slightly soluble in water, which is why we avoid collecting it over water if we wanted to dry sample. Then move on to question D. Question D asks us to state the two commercial uses of gas Y. Carbon dioxide is commonly used in fuzzy drinks to give them their bubbles and as a fire extinguisher since it's denser than air and doesn't support combustion. So it's smoother. It puts off the fire. 12B. Question 12B, our final question on alkenes. Question B tells us that alkenes are a homologous series of saturated hydrocarbons and can exist as isomers. Then part A asks us to define the term homologous series and isomers. A homologous series is a family of compounds with the same general formula, similar chemical properties, and which differ from one member to the next by CH2 unit, showing a gradual change in the physical properties such as boiling point. Isomers are compounds that have the same molecular formula but different structure arrangement of their atoms. So that's the definition there. Isomers are compounds that have the same molecular formula but different structural arrangement of their atoms. Then moving on to question B. Section B asks us to draw any two structures of isomers of pentane, which is C5H12. So pentane has three possible isomers, but we only need two. The first is a normal pentane, a straight chain of 5 carbon atoms, each bonding to each hydrogen atoms to satisfy their 4 bonds per carbon. So for now we know that carbon to be stable, it needs 4 bonds. The second could be two methane butane, 2-methane butane, which is a 4-carbon chain with 1 methyl branch coming off the second carbon. When drawing these, make sure every carbon atom shows 4 bonds in total, whether to hydrogen or to neighboring carbons. Then part C is about the fractional distillation of crude oil, shown in the diagram with the fractionating tower, where crude oil enters at the bottom, heated above the 400 degrees Celsius, and the different fractions are collected at different sites, labeled as the gas, petrol, paraffin, substance X, evaporating oil, wax, and substance Y at the very bottom. Then part C1 asks us to name the substances collected at X and Y. Looking at the position in the tower between paraffin, replicate, and the replicating oil, substance X is the diesel. So substance X is what? Diesel, sometimes called the gassy oil. And substance Y collected at the very bottom below wax is the bitumen, sometimes called the residue. Sometimes it's called what? Residue. Then part C2 asks us for one use of substance C. Y. Butane is commonly used for surfacing roads or roofing materials. Then we're going to question D1. Question D1 asks what we understand by the term cracking. What do we understand by the term cracking? So cracking is a process of breaking down large hydrocarbon molecules into smaller, more useful molecules using the heat and sometimes a catalyst. So that is what cracking is. Then question 2, D2 shows us that 1 octane COH18 is obtained alongside propane in the cracking process as the only products, and access to construct an equation for this process, including the condition. Let's work this out step by step. We need to figure out what large hydrocarbon breaks down into octane and propane. We add the carbon atoms together. Octane has 8 carbons and propane C3H6 has 3 carbons, giving a total of 11 carbons. So the starting hydrocarbon must have 11 carbons. For a saturated alkane with 11 carbons, the formula would be C11H24, following the general formula for alkanes. Let's check the hydrogen balance. Octane is this C8H18 and propane is C360H6. Adding these together gives us 18 plus 6, 8 18 plus 6, which is 24 hydrogen matching the C11 and H24 exactly. So the equation is C11 H24 gives us C8 H11 H18 plus C3 H6. The conditions for this cracking process are heat and the presence of a catalyst. So you write the above arrow. So you need to write about the arrow, the catalyst and the heat. About the arrow. That brings us to the end of question B12, final question. We have 10 marks, and that completes our full walkthrough of the chemistry 57 paper 2, covering section A and 4 questions from section B. Make sure you go back over every section that felt tricky, especially the calculation questions and the equation building steps, since those are where most marks tend to slip away in exams. Keep practicing and you get more confident with every paper you work through. This was your tutor, Robert Mtare. I hope you have learned one or two things. If you have do so, please subscribe, like, and leave a comment. I would love to know which paper you want me to do or which question I should do. Make a video or just leave a comment there indicating the question number and the year, where the question came from. Then I'll be able to help you with it passionately. Or if you can go a bit further, you can WhatsApp me on the number 0968032811, where we do our online teachings, whereby we go deep in this topic, not just answering past papers, but we go deep. We teach the entire topic, then we answer past papers, so you solidify your standing on each. No, at TV online tuitions, time is very what? Cardinal. Time is very cardinal, so we don't waste time on Mtare TV. We only teach what comes in the exam, which is in the syllabus. Thank you for watching. If you haven't subscribed, please subscribe. If you haven't liked, please like. If you haven't comment, please comment. If you haven't joined our online tuitions, please join our online tuitions. This is Robert Mtare, your tutor. Thanks for watching. Bye bye.